So I will today talk about Lipschitz function approximation using DeepSpline neural networks. This is joint work with several people from my lab. And first I will actually introduce what a one Lipschitz neural network is and for what type of tasks they are useful. I don't have a pointer here. Okay, so the architecture is just a general feed-forward architecture which we use here. So we have compositions of affine layers and activation functions. And here the affine functions have a structure as usual. So we have a weight matrix and a bias vector. So nothing special about this. But for the activation functions in this talk, we are a bit more unspecific. So it can be a learnable activation function. And it's in principle, a priori, not necessarily component-wise. So it's just a function from R and K into R and K. So it could depend on several inputs. But for the rest of the talk, to keep things simple, we will stick to component-wise activation functions. And one thing that I really want to stress here is, like, often if you train a network, they are fixed. So you use the same activation for each neuron and in each layer. Here it's really like it can be a different activation for each neuron and in each layer. So we are not tying them together. Then a definition now first, continuous piecewise linear functions. I think everyone has an intuitive understanding what this actually is. But to be precise, we just need that it's like a continuous function, so not really surprising. But there need to exist closed subsets of RD, which if you unite them are the whole space RD again, and they need to have like non-empty intersections like their interiors. So it's like just the polyhedra, which are the decision boundaries. And on each of these regions, the function needs to be affine. They don't need to be connected, so it's like a function can be active on two disconnected regions, or they can all be connected. There's like really nothing enforced here. A really simple case is if we put D and N equal to 1, then we're just back in the setting of linear splines. I guess everyone has seen them in a basic maths lecture. And one particularly nice thing about CPWL functions is that they are stable under composition. So if you compose them, you get back another linear function. I mean, the same would hold like in general for polynomials, but then the order will actually explode. So it's, there are not too many function spaces which are actually closed under composition. So then a brief motivation for using one Lipschitz neural networks. So there is a type of algorithms that's called plug-and-play algorithms, which is used in inverse problems, so for reconstructing images from measurements. And for this type of algorithms, you usually would replace a proximal operator by a denoiser, and if you want to show that the algorithm converges, you actually need to know the Lipschitz constant of your network. Another thing you can do with one Lipschitz neural networks, I think, like at least some of you should have seen the Wasserstein gun, for example, where you just take the dual formulation and then you need to optimize over one Lipschitz functions. You can parameterize them by a neural network, and then the network needs to be one Lipschitz. Then clearly there is something a bit related to the first point, are so-called deep equilibrium and fixed point neural networks with the respective layers. And there the reasoning is just if you do fixed point iterations, like in the simplest case, let's just think about Banach fixed point iterations, then you need that the network is non-expansive. So again, you need some control on the Lipschitz constant. But also if you want to talk about robustness guarantees, it's always helpful to know the Lipschitz constant. I mean, at first glance, this looks quite nice. The Lipschitz constant, it's easy to define. But if we think back on the previous slide about the continuous piecewise linear function, if we want to compute its Lipschitz constant exactly, then in generally we need to evaluate, we need to know the slope on each of the affine regions. And if you think of neural networks, stacking them up, we know that in principle the number of affine regions grows exponentially. So if you just have a general neural network, computing its Lipschitz constant is actually an NP hard problem. So in principle, it's nice to have Lipschitz neural networks, but if we want to use them in practice, we need to think a bit further. There are like some estimation algorithms based on semi-definite programming. I think it's actually also coming from a few people here at EPFL. This is quite nice, but if we want to train a neural network and use this SDP for computing the Lipschitz constant and then want to do backpropagation, it's getting way too expensive. So we need to do something else, and the simplest thing we can do here is restricting the architecture. So we can enforce that the weights are at most 1 under P norm matrix, P matrix norm, and we can enforce that the activation functions are 1 Lipschitz continuous. And then we just know that the Lipschitz constant of the neural network is just upper bounded by the product of the norm of the weight matrices, which is again bounded by 1. But the question now is, okay, we are now in a restricted setting, so we're not having all 1 Lipschitz networks anymore. And what can we say about the approximation properties of this set? Have we lost a lot by making these restrictions or not? This is somehow what I want to cover in this talk. The first thing is I want to show some limitations in this setting. If we just use the ReLU activation function, and here we can actually show that we have some real limitations in the expressive power. So if we assume that I is a closed interval and sigma is a CPWL activation function, which has maximal slope on this interval, so we just have that it's x plus b. You could similarly write the statement with minus x plus b. It doesn't really matter. And outside of this interval, you have that the slope is less than 1 everywhere. So you only have one connected region with maximal slope. Then any neural network with this norm-constrained weights and this activation function has at most 1 affine region on which the Jacobian is maximal. At first, it sounds a bit cryptic, but let's look at the requirements. So we clearly see that ReLU satisfies the requirements. It's just identity on the positive real numbers. And it has slope 0 on the rest, so it fits into the framework. And then on the bottom, I have actually depicted a simple function which has just 3 affine regions. It's just a head function, like a B-spline. And here you see that it actually has 2 regions of maximal slope. So no matter how deep we go with the network or how wide, if we have these constraints, we cannot represent this function. This is like the first thing which is a bit unsatisfying, but like maybe you will ask, okay, like representation, it's always difficult. Like we will never be able to represent a non-piecewise linear function. But on the next slide, we will actually see that also approximation is somehow limited in this setting. So if we look at the function at the 1 Lipschitz functions on some compact domain, then we can show that they cannot be approximated by such ReLU neural networks with these weight constraints, where the matrix norm is chosen as the infinity norm. And I think I will skip the proof here, but it's basically based on the concept of second order total variation, which is just defined as the radon, so the total variation norm of the second distributional derivative. And in the case of CPWL functions, it actually simplifies a lot. Then it's just the sum of the absolute slope changes. This is something just to keep in mind because it will come up again on the next on one of the next slides. So the conclusion so far is that ReLU networks are really not a good choice in our restricted architecture setting. We know that they cannot represent even simple functions. There are also functions that cannot be approximated. The problem with the approximation is that we cannot approximate functions with a high second-order total variation, but there are actually a lot of such functions. So we need to come up with other activation functions which circumvent these issues. And here it would be nice if they are adaptable in the sense that the ReLU is also included if we want to train them. So it will be parameterized activation function. It should be efficient to train. It doesn't help if we have like a framework which is nice theoretically, but not useful in practice. And it should have, in some sense, the maximal expressivity among these component-wise functions. Okay. The unsurprising fact maybe now is that we propose linear splines to achieve these goals. I mean, I'm in Michael Unser's lab, so I guess it's natural to come up with splines. And we phrase the corresponding networks DeepSpline neural networks. And these networks have learnable, component-wise, one Lipschitz linear spline activation functions. And they need to have at least 2 knots, like 2 spline knots. Otherwise, we cannot overcome the issues which I have described before. Here is just an example of such an activation. It can go up and down, but the slope is always 1. And it changes at these knots. Maybe one remark about the implementation. If you want to implement this in this way and just shifting around the knots, it's really difficult, the problem. So for computation, it's actually easier to put like a crit and then just use a B-spline approximation. And then you can put like an additional loss term which enforces that the spline will be sparse. But if someone is interested, I can discuss it a bit offline with the actual implementation. I want to focus more on the theoretical properties here. Okay, like the first nice thing is that we're really more expressive than ReLU neural networks. We have seen before that the ReLU networks have second-order total variation bounded by 2. It would have been in the proof, but trust me on this. And what we can actually show is that if we pick a constant and some direction, then the second-order total variation of our network in this direction can be larger than c. Yeah? So if you give me a function, I can, like a constant c and the direction, then I can give you like a neural network which has like really high second-order total variation in this direction. So a priori, we are not bounded by the same constraints as for ReLU. There is like really an intrinsic problem that if you stack the layers, you cannot create more so you cannot create more variation in the function. And our construction here overcomes this issue. It's more like a pointer. It's not the strongest result, but we can actually say a lot more. In some sense, we can say that we are maximal expressive. So if we assume that D is a compact set, then the DeepSpline neural networks with this weight constraints and linear spline activation functions with exactly 2 knots. Yeah? So we don't need more knots. It really suffices to stay in this setting. Then we can approximate the same functions as with a general neural network with arbitrary component-wise activation functions that are 1 Lipschitz. Yeah? So there could be something really weird just going up and down Lipschitz continuous, nowhere close to such a simple function as a linear spline with just 2 knots. Yeah, and if you take these class of networks, they cannot approximate more functions than already this, let's say, relatively simple setting. Yeah, we don't know if they can approximate all 1 Lipschitz functions so far, but we know in some sense already that among these component-wise functions, this is the class which can represent the most functions. It would be still interesting to look a bit into the approximation properties here, but this is something for future work. So we have seen here that apparently these DeepSpline neural networks are a good choice for approximation. So we actually wanted to benchmark them, started to benchmark them for Lipschitz-constrained applications. This is a bit still ongoing work. So I just have a preliminary example here. So for example, compressed sensing MRI. You have like an unknown image like on the right. Then you apply the Fourier transform to it and then just randomly subsample it to get the data on the left. And then the aim is like to reconstruct the original image. Like in an application, you wouldn't have the image on the right, you would just have the measurements. But it's like a synthetic example here. And then the setting is you can describe it in terms of an equation, A times F plus the noise is equal to the data for the measurement operator A, which here would be just the Fourier transform and a masking. And then in the setting, if you want to solve this inverse problem, one approach would be a variational model. So you take a data term, you take the squared distance between AF and G, and you add like a convex regularizer, which incorporates some prior information, could be, for example, total variation. And then for such convex models, you can actually apply the forward-backward splitting to minimize the variational problem. It reads like the update is just given by applying the proximal operator of your convex regularizer to the gradient step update. So in some sense, this proximal operator is a generalized projection. So what you're doing is like you're doing a gradient step on your data term, and then you're projecting back into the space of nice functions in some sense. And the plug and play idea is to interpret this proximal operator, which I have written in the middle, as actually as a denoising problem under some regularizer. And then, like based on this interpretation, we can say, okay, like we can actually learn really good denoisers, so why not plug in a denoiser? And then we replace this neural network by a learned average denoiser. So just as given here below, it needs to be given by 1 minus t identity plus t times phi. Phi is the denoiser that we learned, and it must be 1 Lipschitz. And if we, this is a parameterization by a neural network that is 1 Lipschitz, and D is the learned denoiser. And then we just replace this proximal operator and do the same iterations. And if the step size of our gradient step is sufficiently small, we know that the method will actually converge. There exist like many more variations of this framework. You could use ADMM, like many convex optimization algorithms, instead of forward-backward. It's just to give like an idea how the method works. And now the big question is like we have this Lipschitz constraint in there, so we need that phi is 1 Lipschitz. So the question is, can we improve such models by using DeepSpline neural networks instead of the usual ReLU network choice. And one thing maybe that I also want to mention here is there is also like a lot of approaches where this constraint is relaxed. So you could, for example, add like a penalization term on the Lipschitz constant, but then you never know the exact Lipschitz constant of the network, and you cannot ensure that it's less than 1. And then you basically lose all of these properties on the convergence result, because they really require that you have this one constraint here. So if you really want the theory to hold, there is no other way than enforcing the constraint strictly, and there are not too many ways to actually do that. Okay. So here is actually a result. So we used a 30% random sampling, Gaussian noise with variance sigma 15. Then we have the architecture is just a convolutional neural network with spectral weight normalization, and we want to see if we can improve by changing the activation functions. As a baseline, I have just the total variation regularization, which I have mentioned before. So it's like a traditional handcrafted model in some sense. So it's a non-learned regularizer. We see that PSNR is around like, let's say 15 on average on the whole bunch of images. Also for different samplings like random, radial, Cartesian, it doesn't really matter which one we take. Then we can use a learned regularizer, which is the third line, which is like a lot better, and it also beats the BM3D plug-and-play setting. So some of you might actually know the BM3D denoiser. People often use it here because it gives nice result, and it tends to work quite often, although the denoiser is not one Lipschitz. But if we use the DeepSpline neural network, train it and plug it in this plug-and-play setting, then we're actually outperforming all of the other choices, which is somehow what we would expect since it's the maximally expressive class of networks for doing this. We are currently, here I have actually also an example. So we can see that there's also like a visual difference. So on the left, I have a zoom in the top part of the image, and we see that in the middle image, so with the ReLU neural network, there's almost nothing left of the center structure anymore. And like with the DeepSpline neural network, we are getting back a bit more. So it's like not only a difference in the PSNR numbers, but there's like also a visual difference. Okay, maybe I skip this application here and conclude now. So what we have achieved so far is on the theoretical side, we have seen that the ReLU networks with weight constraints lack expressivity in this restricted setting. We have seen that linear spline activation functions can resolve these problems. Linear splines are optimal among component-wise activation functions, and there are also non-component-wise activation functions like group sort, householder activations, and at least for spectral norm constraint weights, we are as expressive as these functions. But if you're interested in this non-component-wise setting, we can also discuss a bit later. It's way more involved and getting more tricky to actually compare activations there. On the practical side, we have an efficient training routine available, which should be, I think, on GitHub quite soon, because we're finishing the other paper, and then we will put the link there. I think at the moment it's still private, but it should be like only a matter of a few weeks. We have seen, like in most of our experiments, it's like we're always a lot better than ReLU, so really in all experiments. And if we compare to group sort, we're often like slightly above. And also, like against other non-component-wise activation functions, we are usually slightly above in performance. One advantage of our setting is that it can be inserted into pre-trained ReLU neural networks, just because you can initialize like a linear spline always like as the ReLU activation function, and then you can start training from there. So if you have like invested a lot of time in tweaking a model and you want to push it a bit further, then you can actually just use this as a starting point. And I have just shown briefly the plug-and-play example, but it can also be used for Wasserstein distance estimation and many more things. For this issue, there will be, I think, an archive preprint very soon. Okay, that I will skip here. With this, I want to thank you for your attention, and I'm happy to take your questions.
All right. Questions? Hi, thank you. If I understood correctly, there is a relation between the fact that ReLUs have basically very small second-order total variation norm, and
yes,
the fact that they need large weights in order to approximate more complex functions.
Yes.
So do you have a simple explanation for this relation between the size of the total variation norm of the second order and how big are the weights that you need to use in order to represent complex functions, or?
It's a good question. I think from an intuitive explanation, I have nothing really available here. It's just also like, because this question also sometimes comes up, because like you can represent like any linear spline with ReLUs, but if you do so, you will actually need like a weight matrix which has higher parameters, and depending on how complex your spline is, it actually will be quite a bit larger, like the norm, than 1. So, but I don't have like any quantitative like explanation statement on how it scales, on like what the relation between the actual weight norm is and the second order total variation of this linear spline. So unfortunately I cannot help you there. But it would be a really interesting question actually to look further into this topic.
I agree.
Hello, thank you for the talk. Actually, I have previously talked with Axel where he presented me this idea. It's very cool. I just wanted to ask you to make sure, sorry, for GANs, for graphs, we are really interested in this permutation equivariance property, you know, that must be preserved for
Yes.
Yeah. And so, what I wanted to make sure, so the theoretical results hold for when the same activation function in a layer is applied with the same parameters to every input neuron, right?
No, like our results are like what we can do with our learnable spline activation functions. In principle, we use different activation functions for each neuron and each layer. But I think you might be able to actually, so I think you can actually use the same activation function maybe in each, like for each neuron, by just increasing the number of knots and then like shifting the data back and forth. That I think should work. I mean, like at least it depends a bit on what you're interested in. If it's just like the theoretical properties, you can just like do the construction in this direction, and if you implement it, you can use the same linear spline activation for all of your neurons and just use a high number of knots. I mean, it's like we just gave a lower bound here. So if you really require that it's the same activation for each neuron, I think you can do it, and you will still be quite a bit better than what you can get with ReLU.
Yes, thank you.
All right, I also have a quick question. Maybe I missed it. You gave an example where you showed that the DeepSpline network is more expressive than, let's say, the regular neural network. So is this always strictly true?
It's like only in this weight constraint setting.
Can you find maybe an example where the standard neural network with spectral norms is more expressive than a DeepSpline network?
No, I don't think so. Because like in some sense, like we're including the ReLU setting, because the DeepSpline can always represent a ReLU. So it's like the ReLU, if it will always only be as expressive as the DeepSplines, but never more. But if you have the weight constraints, then your
things also depend on the number of parameters too, no?
Yeah, I'm just assuming that you have like the same architecture. Yeah, so if the only thing that you replace is the activation function, so instead of the ReLU you use a learnable spline with a certain number of knots, then you will always be as expressive as the ReLU with the learnable splines, because you always can choose the learnable spline as the ReLU.
Because in the Wasserstein training, they even not project onto the spectral constraints, but they do spectral normalization, which is even a more...
like if you go into this setting, I can briefly comment on this. So if you want to do this Wasserstein distance optimization, I mean, then there is like this theoretical result that the optimal potential actually has Jacobian norm 1 almost everywhere. So it's if you want to parameterize a network, it's actually good if all the weights have norm 1. And then you also want to use an activation function which is gradient norm preserving, so which is in some sense having a Jacobian which is just a permutation matrix. And like this would be satisfied by group sort, so it works really well in this setting. And in principle, we usually need more layers and parameters to come close to the results. But in principle, we are also able to estimate the true Lipschitz, the true Wasserstein distance in this setting.
Okay.
Yeah,
so maybe
exactly.
we take it off
Yeah,
the
maybe.
rest. So thank you, Sebastian, for the talk. Are there any questions from Japan? I understand that we just ran out of time, but in case there are. Okay, so maybe we thank Sebastian again and then take the next.
Yeah, thank you very much.